Hi, my name is Dr. Deshawn, and in this video we are going to approximate the area of an irregular shape using areas of rectangles, and then on the flip side of the board we're actually going to compute the exact area using limits in the Riemann sum process. So let's take a look at the example we're going to use. We're going to take a look at this parabola here. The function is x squared plus 1. Our interval from 0 to 2, we're going to use 4 rectangles, and we're just going to compute the area to the x-axis. So we have the function y equals x squared plus 1. It's this parabola here. The interval is 0 to 2 to the x-axis, and you can see the boundaries here form a closed region. We want to find the area. So this is, in geometry class you learn the concept of area, but you learn how to find areas of squares, a side squared, or area of a rectangle's base times height, area of a triangle 1/2 base times height, maybe area of a circle is pi r squared. But irregular shapes, well that's, you really don't get to look at that until you get to a calculus class. So let's go ahead and see, let's approximate the area under the curve first. We're going to start with the lower sum, which uses inscribed rectangles. So I'm going to take this region right here. I'm going to use 4 rectangles. So I'm going to break my 0 to 2 interval into 4 equal subintervals. So I'm going to just break it in half and then break it in half again and again. Hopefully they look equal, okay? And then we're going to lower sum, so we want to inscribe rectangles under the curve. So we want to put these rectangles in. So you can see there's my rectangle number 1, here's rectangle 2, here's my rectangle 3, and here's my rectangle number 4. Got 4 rectangles. I'm going to add up the area of these 4 rectangles, and that's going to give me an approximation for the area under the curve. So let me go ahead and start writing that up. So we want to find the area of rectangle 1. All right, we want to find the area of rectangle 2, and we want to find the area of rectangle 3. We want to find the area of rectangle 4. We want to find the area of these 4 rectangles, and we're going to add them together. The area is going to be width times height. For each of these rectangles, it's width times height, width times height. So let's start by finding the width. The width is equal increments here, okay? So the width, we're going from 0 to 2, and we want to compute what the width might be. Some of you can tell by looking at it what the width of each of these rectangles would be, but we do have a formula for that. You could compute it. You could actually compute the width. The symbol they use in your textbook for width delta x is the width, and so the width is going to be your b minus a over n. All right, so the width here is going to, well, a and b are the endpoints of your interval, okay? N is the number of rectangles. So 2 minus 0 for the b minus a over n is 4, okay? So when you simplify this, your width is going to be 1/2, okay? So the width of these rectangles, and what I like to do here in my diagram, so I like to come to my diagram and just count out, there's 1 over 2, there's 2 over 2, here's 3 over 2, there's 4 over 2 there, okay? So the width of each of my rectangles is 1/2, okay? So I'm going to go ahead and write it in my formula because the width is a constant. It's not going to change. My width is equal increments, the way I'm setting this one up, okay? Now the heights of the rectangle, well, those are different, okay? So you can see the height of rectangle 4 is taller than the height of rectangle 3, which is taller than 2, and so on. So let's go ahead and compute the height. First rectangle here, the width is 1/2. What about the height, okay? Well, the height, it hits right here on the y-axis, and we know this is a parabola shifted up 1 unit, so you can tell the height is 1, but we want to put that in function notation. So what is the height of my first rectangle? It's actually the function value at 0. It's f of 0, okay? So it's f of 0. It's when we plug 0 into the function, 0 squared plus 1. So your first rectangle is 1/2 for the width, 1 for the height, so the area of the first rectangle is 1/2, okay? Let's look at our next rectangle, our second rectangle. The width of our second rectangle is 1/2. What is the height of our second rectangle? Well, here's the top of our second rectangle, and look where it hits the curve, okay? So the second rectangle, the height of the second rectangle, the width is 1/2, and the height is going to be the y-coordinate generated at when x is 1/2. In other words, the height of the rectangle is the function value at 1/2, okay? So our second rectangle is f of 1/2, okay? That's my cursive f there. So 1/2 for the width, and then height, 1/2, plug it into the function. 1/2 squared is 1/4 plus 1 gives you 5/4. So your second rectangle has an area of 5 over 8. Okay, your third rectangle, the width is 1/2. What about the height of the third rectangle? It's the y-coordinate, it's the function value at 1. Okay, all right, you can see that the width is 1/2, and what is the height of the rectangle? What's the y-coordinate generated when x is equal to 1. So we call that function value at 1. So it's 1/2 times, plug in 1 squared plus 1 to the function, and you get 2, and half of 2 is 1. And then finally, our fourth rectangle. Our fourth rectangle width is 1/2, and what is the height? The height is going to be the function value at 3/2, f of 3/2, okay? So 1/2 for the width, and 3/2 squared is 9/4, and 9/4 plus 4/4 gives us 13/4. Multiply that by the width of 1/2, and you get 13/8. So what is the first rectangle here? What is our total area? Okay, so total area, lower sum, okay, so total approximate area. All right, what do we have here? Well, we need to add these fractions together. I'm going to go ahead and get a common denominator of 8, okay, so what do I have here? I have 4/8, okay. This rectangle here, the second one, has an area of 5/8. Okay, 1, we're going to call this 8/8. Third rectangle has an area of 8/8. Fourth rectangle has an area of 13/8, okay? So we can keep the denominator, which is 8, and then let's combine those numerators. So 5 and 4 is 9, and 9 plus 8 is 17, plus 13 is 30. So 30 divided by 8, okay, which is, let's say, 3.75. Go ahead and write the lower sum here as a decimal, okay? Just so we can compare it. So we have the 3.75, and that represents the area under the curve, but as you can see from the diagram, the 3.75 is less than the exact area, okay? So where's the exact area in the curve? Well, it's going to be a little bit more than 3.75, okay? Now let's go ahead and compute the upper sum. All right, upper sum means we want the rectangles to be circumscribed. So let's go ahead and start by taking our interval 0 to 2, and we're going to break it into 4 equal subintervals again. 4 equal subintervals, we're going to use 4 rectangles, but this time we're going to let our rectangles fall outside the curve. Okay, so we're going to sketch the rectangles so they're outside the curve. This is going to generate an area under the curve that's more than the exact area. So let's go ahead. This is our rectangle 1. This is going to be our rectangle 2. Here's rectangle 3, and here's rectangle 4. And we want to approximate the area using these rectangles. Okay, so here, let's go ahead and write this up. So we want to get the area of rectangle 1. We want the area of rectangle 2. We want the area of rectangle 3. And we want the area of rectangle 4. Okay, and so it's going to be width times height, and width times height, width times height, width times height for each of these 4 rectangles. All right, we want to go ahead and compute the area. All right, so the width, well, the width is 0 to 2, and we're breaking it into 4 equal subintervals. So what do we do with the width? Well, we've already computed over here. Here's a formula. I like to write it along the scale here. So we're going to do increments of 1/2. There's 2/2. Here's 3/2. There's 4/2. The width of each of these rectangles is 1/2. So we can go ahead and write that in. So the width of each of these rectangles is 1/2. All right, we're using equal subintervals. Now, what about the heights of the rectangle? You should clearly be able to see that the heights are different, okay? Rectangle 4 is taller than rectangle 3, and so on. So what about the heights of the rectangle? Well, let's take a look at our first rectangle. Here's the top of the first rectangle, okay? So where does this top of the first rectangle hit our function? What is the height, okay? All right, the width is 1/2, and what about the height? Well, it's the y-coordinate associated at 1/2. It's the function value at 1/2 for this one, okay? So your width is 1/2, and your height, when you plug 1/2 into this function, 1/2 squared is 1/4, plus 1 is 5/4. So your first rectangle has an area of 5/8. All right, your second rectangle, okay? So the width of the second rectangle is 1/2. What is the height of the second rectangle? What's the height? Look at the top of the second rectangle. You can see where the top of the second rectangle is. Look at the line segment forming the top of the second rectangle, okay? This vertex is out here like in midair, but this is where it hits the curve, okay? So 1/2 for the width. What about the height? Well, the height is going to be the y-coordinate, okay? You can see where the height is, where it hits the y-axis when x is 1. So when x is 1, it's where it hits the y-axis. So it's the function value at 1. Just trying to draw this so you can see it. So you have 1/2 for the width, and when you plug 1 into the function, 1 squared plus 1 gives you 2, so half of 2 is 1. Your third rectangle, the width is 1/2. Your height is going to be the function value at 3/2. So it's the function value at 3/2. So you take 3/2 squared is 9/4. 9/4 plus 4/4 gives you 13/4. So you have 1/2 for your width, you have 1/2 for your width, and you have 13/4 for your height. The area of the third rectangle is 13/8. And then finally your fourth rectangle. So your fourth rectangle, the width is 1/2, and the height of your fourth rectangle is going to be the function value at 2. Okay, so it's going to be f of 2. When you plug 2 into the function, 2 squared is 4, 4 plus 1 is 5. So 1/2 for the width, 5 for the height. So you end up with 5/2. Okay, now what do we want to do here? We want to get a total lower sum area approximation. Okay, so based on this, total lower sum area approximation. Okay, so let's go ahead and get a common denominator so we can compute. We're going to use 8 again for the common denominator, so 5/8. Okay, and then so 1 is the same thing as 8/8. The area of our second rectangle is 1, which is 8/8. The area of our third rectangle is 13/8. All right, and then the area of our fourth rectangle, 5/2. Let's write this over 8 so we can combine. So 2 goes in 8, 4 times 5 is 20, so 20/8. Okay, so you keep the denominator, which is 8, and you combine the numerator. So 5 plus 8, 13, and 13 plus 13 is 26. 26 plus 20 is 46. Okay, so 46/8. 8 goes into 46, so 5.75 if you change this to a decimal. Okay, and that's your upper sum. Okay, so this is what your upper sum is. So where is the exact area? Okay, so where might the exact area be found? All right, well, your lower approximation for the area under the curve is 3.75. All right, and your upper approximation is 5.75. So the exact area is somewhere in between. Somewhere in between. Okay, not necessarily the average of the two, but somewhere in between. So the concept is this: the more rectangles you use, the closer you're going to converge to the exact area. Okay, so you use, what if we, instead of using 4 rectangles, what if you used 100 rectangles? Okay, so if we used 100 rectangles, we're going to be converging onto the exact area. All right, we want to actually compute the exact area under the curve. So how many rectangles do we need to use? We're going to need to use infinitely many rectangles. And all right, so we're going to put infinitely many rectangles in here. We're going to add up the areas of infinitely many rectangles. Okay, is that even possible to do? Of course it's possible to do. We're going to do this right now. So let me go ahead and flip the board over. On the other side of the board, we're actually going to compute the exact area under the curve. So you see where the approximations are, so you know where our answer is supposed to lie. All right, but let me go ahead and flip over the board, okay, because I have it set up over here. Now let's go ahead. We're going to compute the exact area under the curve. All right, we want to compute the exact area under the curve. Here's a diagram, okay, so 0 to 2. We know we've got a finite area there somewhere between, 3.75 and 5.75. This is your formula to compute the exact area, okay? You're going to take the limit as n goes to infinity, a Riemann sum, I goes from 1 to n, width times the height. Now, just to understand what this formula is doing, the width times the height is the area of your rectangle. So you're going to find the area of rectangle. We're going to start with the first rectangle, then we're going to take the second, the third, the fourth, the fifth, the sixth area, seventh area, eighth area, and so on. We're going to keep it. What are we going to do with all these areas of the rectangles? Well, summation in mathematics class, the Riemann sum, this sigma notation means add them together. So we're going to add together all the areas of the rectangles. How many rectangles we're going to use? We're going to use n rectangles, but we're going to let n go to infinity. Okay, so when we have methods that we've learned to do all this. So let's start with our curve here. Let's start by getting the pieces that we need. All right, so to get this exact area under the curve, we are going to take the limit as n goes to infinity, and we have summation. I goes from 1 to n, the width times the height. Okay, the width. All right, I'm going to come off to the side over here. How do we compute the width? Okay, the width, also called delta x. Your formula for the width is b minus a over n, just like we did on the other side of the board, b minus a over n. Okay, subtract the bounds, so it's 2 minus 0 over n. Okay, so it's going to be 2 over n, and that's what the width is. Okay, so the width is 2 over n. We have to leave the n. We can't put a number n because we're going to let the n go to infinity. We're going to use infinitely many rectangles here. So this is how you would compute the width. It's very formula driven. This is how you compute the width. All right, so we are going to compute the width. This is going to be 2 over n. All right, now the height, how do you compute the height? Well, the height, you're plugging into the function. That should make sense because on the other side of the board, to get the height, we had to plug numbers into the function. Plug into the function the left bound plus your width, delta x, okay, times your ith interval, okay? So here's a formula, very formula driven, okay? So this is how we're going to compute the height. We're going to plug into the function the left bound, because we need to know where to shift to. The left bound here is 0. So you take the left bound plus your width is 2 over n, and then it's times the ith interval, okay? So, and we're going to compute this. I like to do this off to the side, so I'm going to compute this, okay? So I'm going to take 2i over n, and I'm going to plug it into the function, 2i over n plus 0. So, and what do we do with this? We plug it into our function. F of x is x squared plus 1, so we want f of 2i over n. So our function says take it, square it, and add 1 is what our function says. We want to plug 2i over n into the function and compute it. So 4i squared over n squared plus 1, and this is what our height is going to be. Okay, so here is the height for this problem. Like I said, very, very formula driven, okay? So you should look at the theory behind why all this works. I'm trying to cover it a little bit here with these examples, but very formula driven. So that's how you compute the width, that's how you compute the height. So for this problem, our height is 4i squared over n squared. All right, so it's 4i squared over n squared plus 1. That's what we've got, okay? Now, what I like to do next, okay, we're going to come over here and we're going to compute this, okay? We're going to compute, there's my width times my height, okay, for this region right here. Width times the height, and so we're going to start with 1 and 2 and 3. We're going to find all the areas of these infinitely many rectangles, add them together, and it's going to land on the area under the curve. I like to start by distributing the 2 over n. There's many, many different ways to go through the algebra process. I like to start by distributing. So what do we have for the area? Okay, we've got the limit, n to infinity, summation. I goes from 1 to n. I'm going to distribute. So 2 times 4, I have 8i squared over n cubed, and then distribute here, and I have 2 over n. So I'm right here. All right. And then as soon as we're done with this step, we want to go ahead and use our summation formulas. You have summation formulas. There's I cubed, I squared, I to the first, constant, and we have summation formulas that you may have to go and look up, but we're going to go ahead and put our summation formulas in for the i's, okay? So I'm going to substitute summation formulas in. When you substitute summation formulas in, the Riemann sum expression can go away. So you have the limit as n goes to infinity. So I'm going to take the 8 over n cubed, and I'm going to substitute in the I squared formula, okay? And then I have the 2 over n, and I'm going to substitute in the constant formula. So we have formulas, summation formulas is what they're called, all right? So summation formula for I squared is n times the quantity n plus 1 times quantity 2n plus 1, all that's over 6. And then anytime you have an expression here, a term without any i's on it at all, that gets multiplied by n, okay? So we have summation formulas when you learned Riemann sums, and so you want to put the summation formulas in. When you put the summation formulas in, you're substituting them in for the Riemann sum, so the Riemann sum comes out, okay? All right, so your Riemann sum of I squared is this quantity here, n plus 1, 2n plus 1 over 6, and your summation for a constant is n. All right, and then we want to simplify here, okay? So we want to take the area, we're taking the limit, n goes to infinity, okay? Let's go ahead and simplify. Let's see what we can do to simplify. So you've got the 6 and the 8 here, so 2 goes into 6 3 times. 2 goes into 8 4 times. One of these n's cancels, so I'm going to cancel one of the n's away, all right? And then expand, so we're going to have to distribute and distribute the 4. So 2n times n gives us 2n squared times 4, so 8n squared, all right? And then what do we have? Middle term is 2n plus 1n, 3n times the 4 out here, so you have 12n, okay? And then 1 times 4 is 4, okay? And the denominator, you have 3n squared, All right, and then over here, I have 2n over n, okay, because I left it unsimplified. So I have 2n over n. I know you can cancel those n's out, but I'm going to get a common denominator. Okay, so I'm going to need a common denominator, so I might as well leave that there as a place filler. So let's take the area. So it's the limit. Okay, so n goes to infinity. All right, let's get a common denominator. So it's going to be 3n squared. All right, and then common denominator is going to be 3n squared. All right, so our first fraction, we have the 3, we have the n squared. So all you really need to do is just bring down that numerator. Our second fraction, we have an n, but we want 3n squared. So we need to still multiply by a 3 and an n. So numerator, denominator, we still need to multiply numerator, denominator by the 3 and by the n, okay? So your new numerator becomes 3 times 2, so it's going to be 6n squared. And so there's your new numerator, okay? Let me see if I can write down here one more step. So we want to keep the denominator, so the area, it's going to be the limit, okay, n to infinity. We want to keep the denominator, which is 3n squared, and we want to combine the numerators, okay? So when we combine the numerators, 8n squared and 6n squared, we have 14n squared, okay, plus 12n plus 4. All right, so we have this, okay? So finally, we can go ahead and take the limit. Powers are the same, so 14 thirds, okay? So 14 thirds, and if you want to write this as a decimal, 14 divided by 3, that would be what? 2.6 repeating, okay? So there's 2.6, okay? Whoops, I'm sorry, 4.6 repeating. So there's 4.6, okay? 3 goes into 14, 4 times 3 is 12, so 4.6 repeating, okay? So this is what we came out with. So 14 thirds or 4.6 repeating, and that is the exact area. That's the exact area under the curve, that region right there, okay? So that is what the area is. So, you know, we, on the other side of the board, we got the lower sum of 3.75, we got the upper sum of 5.75, so we know the exact area is more than 3.75, less than 5.75, so, and we're using rectangles, approximate the area under the curve using rectangles. So, you know, if you want to get the exact area of an irregular shape, you would have to use infinitely many rectangles, and this is the process that you would use to go through that. All right, that's about it. So thank you so much for watching. Appreciate it. If these videos do help, please subscribe. And till next time, take care. Thank you. Bye-bye.